Our job today is to design and implement a neural network to classify simple images in our dataset of checkerboards, bright lines, and triangles. So where do we even begin? Well, when we finished talking about perceptrons in the first section of the course, we handcrafted a neural network to predict whether it's a good day to play tennis. Using a similar thought process, if we had to devise a neural network to classify simple images, a network design we might come up with could be something like this. A quick note about terminology here. We have 3 layers of nodes. The layer to the far left is the input layer, the layer to the far right is the output layer, and the layer in the middle is what's called a hidden layer. Also recognize the perceptrons embedded in this model. Since this thing has 2 layers of perceptrons, some people would call this model a multi-layer perceptron. So how did I dream up this network? Well, our data has 4 features, so I know for certain it should have 5 input nodes, 4 feature nodes plus a bias node fixed equal to 1. I really don't know how many nodes the hidden layer should have, but I arbitrarily guessed 5, one of which is another bias term. I also don't know how many hidden layers I should chain together, but to keep things simple, I decided to start with just 1 hidden layer. And for the output layer, I know it has to have 1 node because I'm designing this model to be a binary classifier, just like a typical perceptron. Later on, we'll see how we can extend this model to have multiple output nodes. The big question here is, what should the weights be? You can see I conveniently excluded them. We'll get to that in a second. By the way, this is how neural networks are typically depicted, but I like to add a set of nodes whose job is to sum the weighted inputs into a scalar, and then pass that scalar onto these subsequent nodes, which look at those incoming signals and decide whether to fire or not fire. Meaning, they look at the incoming signal, and if it's greater than 0, they pass on the value 1, otherwise they pass on the value 0. Let's run through a simple example just to make sure we're on the same page as to how this works. First, let's assume that somehow we've come up with the following weights for our network. Then the first simple image in the training data looks like this. So for training sample 0, the input pixels would get set to 200, 52, 58, and 199, plus the bias term which is fixed equal to 1. Then if we focus on the first perceptron, we'd calculate a signal which we'll call z equal to the weighted sum of the inputs, which ends up being 12.37. So then we could do the same thing to calculate the signal going into every hidden node. And then, per the usual perceptron rules, the first 2 hidden nodes would fire because their signals are greater than 0, and the last 2 hidden nodes wouldn't fire because their signals are not greater than 0. So the outputs of the hidden layer, 1, 1, 0, and 0, plus the hidden layer bias term, become the inputs to the next layer, the output layer. So then we just do the same exact thing and ultimately calculate our prediction, Yhat, for this sample as 1. Notice that once again, we have a multi-class classification problem because we have 3 target classes and a binary predictor, because for a given input, our model spits out a 1 or a 0. So we have to simplify our problem. For the time being, let's just try predicting whether each image is a checkerboard or not a checkerboard. Challenge: implement a neural network class with this structure. Give it a fit method and a predict method, just like we did with our perceptron class. For the fit method, randomly guess 10,000 different sets of weights and keep the weights that produce the best predictions. Here's the code I came up with. But before I explain it, I think it'll help to add more context to the network diagram we're working off of. First of all, what does our input look like? Well, we've got 2 matrices, i.e. NumPy arrays. X is a tall matrix with n rows and 4 columns, and Y is another tall matrix with n rows and 1 column. However, in my code, X is a 2D array, but y is a 1D array, so keep that in mind. Next, X has 4 columns, but the input layer of our neural network has 5 nodes. So just like we did with our perceptron model, we immediately convert the input X into a matrix which is just a copy of X with a column of 1s appended to the end. Next, let's deal with this first set of edges, i.e. the weights. Each weight has a natural subscript pair, from node to node, or to node from node. People make different choices here, but I'll go with from node to node. So then the weights can be organized into a matrix, i.e. a 2D array, like this, where the number of rows corresponds to the number of from nodes, and the number of columns corresponds to the number of to nodes. Another way to think about the weight matrix is that each column corresponds to a perceptron in the first layer of perceptrons. The second weight matrix follows the same pattern, but then we have this issue of distinguishing the first weight matrix from the second weight matrix. So we'll introduce superscripts like this. Next, we'll deal with these bold dots that represent the weighted sums of the prior layer of nodes. We'll label these guys Z, also with a superscript to distinguish the first layer of Z's from the second layer of Z's, and subscripts I and J, where I represents the ith input sample, and J represents the jth signal in the respective layer. So the Z matrices end up looking like this. Next, we have the hidden layer nodes. You may have noticed a striking similarity between the hidden layer and the input layer. They do the same exact thing, just at different stages in the network. In other words, the hidden layer nodes can be interpreted as inputs to the rest of the network. So, just as we labeled the input layer like this, we can label the hidden layer like this. And then of course, we'll give these guys superscripts to distinguish between them. At this point, we've notated everything in our network, but we should clarify some definitions. Let's focus on Z1. Picking out the first element of Z1, we see that it's equal to the first row of X1 dotted with the first column of W1. Similarly, Z112 equals the first row of X1 dotted with the second column of W1. Following this pattern, you can see that the matrix Z1 equals the matrix product of X1 times W1. Similarly, the matrix Z2 equals the matrix product X2 times W2. Now, what about X2? Ignoring the last column for a second, X2 equals 1 where Z1 is positive and 0 otherwise. A functional way to write this is h of Z1, where h is the Heaviside step function, defined as h of x equals 1 where x is greater than 0 and 0 otherwise. So we get X2 equals the matrix h of Z1 with a column of 1s appended to the end. And then y hat is defined nearly the same way. Lastly, I should mention that the process of making these calculations all the way from input to output is what's called the forward pass. Let's see how I implemented this in code. The first thing I do is I define a helper function called Heaviside, which inputs a 1D array of real numbers, x, and outputs a corresponding 1D array of 1s and 0s using the Heaviside step function. Then I define a neural net class with 3 methods. Init, which allows me to initialize a neural network, optionally passing in W1, W2, and Y classes ahead of time if I already know what they should be. Fit, which does the heavy lifting of learning the best weights given some training data. It's also in this method where I determine the structure of the network. I'll explain that in a second. And then predict, for making predictions on new data, assuming we've already trained the network. So the fit method takes 5 arguments: x, a 2-dimensional NumPy array of real-valued features; y, a 1-dimensional NumPy array of 2 distinct target classes like 1s and 0s, trues and falses, or a's and b's; hidden nodes, a scalar that says how many hidden nodes to use in the hidden layer, excluding the biased node; guesses, which is by default set to 10,000, which means how many guesses to make, and seed by default set to none, an optional random seed you can pass in to get reproducible results. The first part of the fit method is just recycled code from the perceptron class, where I validate the input and create y01, which converts the inputted y array to an array of zeros and ones. Then I initialize a random number generator. I set x1 equal to x with a column of ones appended to the end of it, and then I set up variables to track the best weights and accuracy. Next, I enter a for loop that runs guesses iterations. Inside the for loop, I start by randomly assigning weights to W1 and W2. The only sneaky thing about my code here is since I use uniform random weights between -1 and +1, and I know my inputs vary between 0 and 255, I want to pick random biases in the first layer that could overcome the inputs, meaning I wanted the range of my bias term to be the same as the range of the sum product of the input features and weights. Otherwise, the bias is rarely going to have any effect on the model. After I set up the weight matrices, I do some basic matrix math to determine Z1, X2, and Z2, and ultimately Yhat. Again, this is what's referred to as the forward pass. It's pretty critical that you understand what's happening here, so if you don't, I suggest you pause the video and step through the code with some toy data until it makes sense. And then from here, I just measure the accuracy of the current weights, and if they're the best ones seen thus far, I store them in the variables best W1 and best W2. Once the loop completes, I just update the class attributes Y classes W1 and W2. And then the predict method is pretty self-explanatory. It's just a forward pass on some new X data using the weight matrices stored as class attributes W1 and W2. Let's see this thing in action. I'll start by reading in the symbol images training and test data. Then I'll initialize a new neural network object and fit it to the training data, setting y equal to train.label == checkerboard. And now I can evaluate it by making predictions on the test data. You can see it's about 70% accurate in classifying checkerboards.